Alright, so now let's practice using these property tables to find some properties, okay? And first we're just going to practice looking at saturated liquids or saturated vapors. Those are like 0.2 or 0.4 on these previous diagrams. Where are we? Sorry, right here. You know, if it is a saturated liquid, it's 100% liquid, but it's about to vaporize. If it's saturated vapor, it's 100% vapor, but it's about to condense. And those are just the subscripts, you know, HF. The subscripts F for saturated liquids, the subscripts G in those property tables for saturated vapors. But you have to know which table to use. Are we in SI or English units? Is it water or refrigerant? And if it's saturated, we're using tables 4 and 5 for water. Tables, what was it, 11 and 12 for refrigerant. Okay, so here we go. We've got a rigid tank. Contains 50 kilograms of saturated liquid, water at 90 degrees C. Determine the pressure in the tank and the volume of the tank. So before I even really, think about what it's asking for, because I know that it is, well, first of all, sorry, let me start out. This is, I see the degrees C and I see kilograms. It is SI units. So that tells me it is Appendix 1, not Appendix 2. Appendix 2 is, table A, 4E, 5E, 6E, 7E. This is not English units. This is SI units. All right. The next thing that I see is water. Water. So that tells me it is tables 4, 5, 6, 7, right? A 4, 5, 6, 7. Not 11, 12, 13. 11, 12, 13 is for a refrigerant. And then it tells me it is saturated liquid. So it tells me it is saturated, so I know it is 4 or 5. Right? So I know it is 4 or 5. And then finally it gives me the temperature. So if I'm given the temperature, I know I'm at 4. I know I'm at 4. So I'm going to go to table A4. And so, here we have a listing of the property tables. Don't get too bogged down in all the other ones, but we're going to use 4, 5, 6, 7, and 11, 12, 13 for now. And so do you see why I am at table A4? Because it's saturated, and I'm told the temperature. It's saturated, and I'm told the temperature. So go to table A4. Hopefully you're faster kind of, getting there than I am. All right, so here is a property table, and I was told it is saturated liquid, right? I was told it was saturated liquid, so I'm really looking at these subscript F values right here, and I'm told at 90 degrees C, and I'm told at 90 degrees C. So, these values right here might be some of the values that I want, right? Okay, so let's see what it is that I want. So if you go back to the problem statement, it says determine the pressure. Well, if it was saturated liquid, or if it was saturated vapor, or if it was a mixture of saturated liquid and vapor, it only has one temperature. It only has one pressure for that temperature. It only has one saturation pressure for that temperature. So whether this was saturated liquid or saturated vapor or a saturated liquid vapor mixture, its pressure would be 70.183 units are up there, kPa. So let's go back to our notes and say the pressure. So we are looking at table A4. Maybe go and write what table you're looking at to help me know if you were at the right property table or not. 70.183 kPa. And go ahead and, some professors would want you to round that to some significant figures. I just, whatever's on the table, go ahead and give it to me. So 70.183 kPa right there. Determine the pressure in the tank. We've got it right there. All right, determine the volume of the tank. So next thing, volume would be equal to what? Well, first of all, do not use PV equals nRT or anything like that. That's for an ideal gas. This is not a gas. This is a mixture. We haven't even gotten to PV equals nRT. So don't try to do something like that, because this is not an ideal gas. That's an ideal gas equation. But I can use property tables, right? I've got a property table that has some interesting properties in it. If we want the volume of the tank, going back to our property tables, I could tell you the specific volume. Okay, maybe that's where we're at, right? I can't tell you the volume right now, but would you be interested in the specific volume? I know that the specific volume is 0.001036 meters cubed per kilogram. Maybe I can take that and use that in order to get the volume. Do you see where I'm going at with this? It's asking for the volume. I'm going to get the specific volume from the property table, but look at the units. Think about specific volume versus volume. Can I kind of convert that? Here we go. Let's go back to our notes here. All right, from the property table, table A4, VF, the specific volume, is 0.001036 meters cubed per kilogram, but I want the actual volume. Do you see how the units help give you a hint here? But also, specific volume is total volume divided by mass. Right, that's what specific. Specific is divided by mass. The units tell you it's divided by mass. So if we wanted this big V here, what would we do? We would take the specific volume times the mass. Big V equals specific volume times mass. You don't have to memorize that. I think the units told you that, but also maybe just know that specific properties are total properties divided by mass. All right, so let's see about this. I'll take that specific volume, 0.001036 meters cubed per kilogram, and the problem statement told me we had 50 kilograms of it. There we go. I've got a volume of 0.0518 meters cubed. 0.0518 meters cubed. Do you see how specific volume is how we're going to get volume? Or sometimes in a roundabout way, they give us the specific volume by us knowing the volume and the mass. So there we go. That's it for problem number 1. That was a saturated liquid, water, at SI units at that temperature. Let's look at the next one right away. All right, so we've got a piston cylinder device. It contains 2 cubic feet of saturated water vapor at 50 psi pressure. All right, the first thing I see, English units. So this is in Appendix 2, all those A4E, A5E, A6E, or maybe 11, 12, and 13E. All right, so we're in English units. We are water. Water, not refrigerant. So I'm looking at a 4E, 5E, 6E, 7E. All right. It is saturated vapor. All right, but whether it was saturated vapor or saturated liquid or a saturated mixture, I would still be in tables 4E or 5E. So English told me E. Water told me 4, 5, 6, or 7E. Saturated tell me, okay, it's 4 or 5. And we are told the pressure is 5E. Oops. The pressure is 5E. So table A5E is the one that we are going to use to find all this. Saturated vapor tells me look for the subscript G. VG, HG, UG, SG. Any of the property tables that have subscript G is what we're looking for. So let's find that property table. I'm in Appendix E, so I'll go to the whole second half, which is a long ways away. Here we go. Here's Appendix 2. Right, see all these E's. 4, 5, 6, or 7E if we're looking at water. 11, 12, 13 if we're looking for refrigerant. We're looking for water. What do we say? 5E. Water, saturated, and we're given the pressure. So 5E. Let's go there. That was 4E, 4E. Here's 5E. All right, we are told it's at a pressure of 50 psia. 50 psia. So anything right here. I would use a ruler, right? I would use a ruler if I were you to put on top of this to make sure you're following along the right line right there. All right, and first thing it asks for is determine the temperature. Well, there it is. If it is saturated, then there's only one temperature for that pressure. There's only one pressure for that temperature. If it is saturated, it's a 1-to-1. You know, there's only one answer, whether it's saturated vapor, saturated liquid, saturated mixture. If it's at a pressure of 50 psia, it's at a temperature right here at 280.99. Let's look, degrees Fahrenheit. 280.99 degrees Fahrenheit. So the temperature is the saturation temperature, 280.99 degrees Fahrenheit. All right, now determine the mass. Mass is not a property on the property table, right? Mass is not a property on the property table. So I can't read mass from that property table. I could only read, let's see, what can I get from property tables? Specific volume, internal energy, enthalpy, entropy. Okay. What else did it give me? Do you see back in the problem statement, it gave me the volume. Remember what we did? We're going to do this this is a big thing, is we're given the volume, 2 cubic feet in the problem statement. Do you think we could take the volume and take this right here, the specific volume right there, 8.5175, look at our units, do a little bit of manipulation, and take the volume, and from the property table, the specific volume, I bet from that we can get the mass. All right, I bet from that we can get the mass. All right, so specific volume, 8.5175 cubic feet per pound mass. So the V subscript G is 8.5175 feet cubed per pound mass. I know that little v equals big V over M. What if I take the big V divided by little v? Big V divided by little v. Let's see if the units work out here for us. Big V, 2 feet cubed divided by 8.5175 feet cubed per pound mass. The feet cubes cancel out. Pound mass is in the denominator, right? Almost like two negatives make a positive. If it's in the denominator, then it's really in the numerator. So yes, my units do work out. I've got 0.235 pound mass. That would be the mass in the piston cylinder device. All right, so you see how that specific volume is kind of a roundabout way of volume and mass. Don't forget this right here. Make sure you know it's on your. Make sure it's on your formula sheet, or just know it. Specific volume, total volume divided by mass. All right, let's do another one. We're still looking at just saturated liquid or saturated vapor. Saturated liquids are the properties with the subscript F. Saturated vapor, properties with the subscript G. All right, we've got a mass of 200 grams. Look at that, 200 grams, not kilograms. 200 grams of saturated liquid water is completely vaporized at a constant pressure. So it is completely vaporized. So we're saying it goes from saturated liquid to saturated vapor. Saturated liquid to saturated vapor. All right, determine the volume change and the amount of energy transferred to the water. Determine the volume change, amount of energy transferred to the water. All right, so we're at a constant pressure. If we were to look at our PV diagram or something like that, we're kind of going from point 2 to point 4 at a constant pressure. And it's trying to tell us the volume change. It's telling us the volume change. Well, I could go to a property table. Which property table? Because of grams and kPa, I know I'm in SI units. I know that it is water, not refrigerant. I know that it is saturated. We're going from saturated liquid to saturated vapor. And I am given the pressure, so that is table A5, right? Table A5. So from table A5, am I going to be able to read the volume change from saturated liquid to saturated vapor? No, but I bet I can get the specific volume change, right? The specific volume from liquid to the specific volume from vapor. That's how we can find the total volume change. All right, so going to table A5. Let's go back to our property tables. Go all the way back to table A5. That's table A4, A4. And here's table A5. I am water, SI units, saturated, at a pressure of 100 kPa. 100 kPa right here. So any of these values right here would be okay. So if I want the volume change, I'm going to first take the specific volume change. I'm going to take the specific volume change. 1.6941 minus this right here. Now, some professors would say you could neglect this because it's on such a smaller order of magnitude than that. But I want you to go ahead and do the little bit of math. Your answer won't come out much differently. But let's take 1.6941 minus 0.001043 to get the change in specific volume. All right, change in little v would be Vg minus Vf. Change in little v would be 1.6941 minus 0.001043. The answer, 1.6931 meters cubed per kilogram. That is the change in specific volume, but I want the change in actual volume. So I would, let's see, little v is big V over m. Big V is little v times mass, right? Big V times mass. So 1.6931 meters cubed per kilogram times 0.2 kilograms, right? How much mass do I have? 200 grams. That's 0.2 kilograms. So that would be a change. This is a change in volume. The change in volume would be 0.3386 meters cubed. 0.3386 meters cubed. That is the volume change. Okay? Okay, part B. We haven't really talked about this. Let's talk about this now. The amount of energy that the water needs, the amount of energy that the water absorbs, the amount of energy transferred to the water if we change from saturated liquid to saturated vapor is really asking for the change in enthalpy. This is really asking for the change in enthalpy, okay? If you want the energy change of a closed system that is changing volume, which is what this is, we don't want the change in internal energy, we want the change in enthalpy. I briefly mentioned this, but enthalpy combines the energy change in internal energy with the energy change in volume. There is some sort of flow work energy change. But anyway, the amount of energy transferred is the change in enthalpy, which is also known as the latent heat of vaporization. How much energy is needed to vaporize this? All right, so it wants a change in enthalpy, and I can get that from the property table, right? I can get that from the property table. I can look for enthalpy of a saturated vapor, enthalpy of a saturated liquid. Here we go, is enthalpy right here. Now, you can see, I don't think we've mentioned this before, you can see if we take this Hg minus Hf, that is what this middle column is giving us. So for internal energy, for enthalpy, and for entropy, you see the subscript Fg, subscript Fg, that is just the difference, the change in vapor minus liquid. So that we don't have to do, because we're going to use that value quite a bit, especially a little bit later, so that we don't have to subtract those ourselves. Here we go. That right there, 2257.5 is the change in enthalpy from liquid to vapor. All right, let's go back to our notes. The change in enthalpy, we call it H, is Hg minus Hf or Hfg. It was listed in there, 2257.5 kilojoules per kilogram. This is a lowercase h. Look at the units here. This is specific. This is specific. It doesn't really specify, and if it doesn't specify specific, it's really asking for total. Look. It's really asking for total, capital H. So we need to multiply that times mass, just like we've kind of been doing. If we have specific, the property tables give us specific properties. Multiply them times mass to get the total properties. So we take 2257.5 kilojoules per kilogram, and we have 0.2 kilograms, 451.5 kilojoules. That is the total energy transferred to the water, the total energy absorbed by the water, the total energy needed to transform the water, the latent heat of vaporization of the water at that pressure right there. All right, so you see how we can use these property tables that have subscript F for liquid, they have subscript G for vapor, and the change from F to G is many times listed down the middle right there as subscript Fg, in case we need that.